What if everything we thought we knew about the universe's expansion was incomplete? Picture this: scientists armed with the most advanced telescopes, measuring the cosmos with unprecedented precision, only to find that the numbers refuse to line up. At the heart of this cosmic mystery lies the Hubble constant, a single number that holds the key to understanding how fast our universe is stretching apart. It's supposed to be one of the most fundamental constants in cosmology, a cornerstone of our cosmic maps. But here's the twist: after decades of meticulous observation, we've stumbled upon not one or two, but 25 glaring anomalies in its measurements. These discrepancies aren't just minor glitches, they're cracks in the foundation of modern astronomy, suggesting that something profound and unexplained is lurking in the fabric of space itself. Think about what that means for a moment. The Hubble constant isn't just some abstract equation. It's the universe's speedometer, telling us how quickly galaxies are racing away from each other. When Edwin Hubble first uncovered this expansion nearly a century ago, it revolutionized our understanding of the cosmos. But now, as we peer deeper into the void with tools like the Hubble Space Telescope and gravitational wave detectors, the numbers we're getting don't agree. Some measurements suggest a faster expansion, others slower. The difference might sound small, but in the precise world of astrophysics, it's like trying to fit a square peg into a round hole. Something just doesn't add up. And with 25 distinct anomalies muddying the waters, scientists are facing a puzzle that could rewrite the rules of the universe as we know them. So what's really going on? Could these anomalies be pointing to new physics, hidden dimensions, or even flaws in our most cherished theories? The stakes couldn't be higher. If the Hubble constant's inconsistencies hold up, they might force us to rethink dark energy, the Big Bang, and the ultimate fate of everything. That's why this isn't just a story about numbers, it's a detective story spanning the cosmos, where each clue leads us closer to either a groundbreaking discovery or a humbling reminder of how much we still don't understand. Buckle up, because we're about to dive into one of the most tantalizing mysteries in modern science, where every anomaly is a breadcrumb leading us deeper into the unknown. One of the most baffling inconsistencies in the Hubble constant saga is the glaring mismatch between measurements taken close to home and those from the edge of the observable universe. Right in our cosmic backyard, astronomers rely on pulsating stars called Cepheid variable celestial lighthouses, whose predictable brightness fluctuations let us gauge distances to nearby galaxies with remarkable precision. By tracking how fast these galaxies are receding from us, scientists can calculate the Hubble constant directly. But when they compare this local measurement to the value derived from the cosmic microwave background, the faint afterglow of the Big Bang itself, the numbers refuse to agree. The CMB method, which captures the universe in its infancy, suggests a slower expansion rate, while observations of nearby galaxies point to a faster one. This discrepancy isn't just a minor rounding error, it's a gap of about 8%, a chasm in cosmological terms. Picture two clocks, both meticulously crafted, one ticking slightly faster than the other. At first glance, the difference seems small, but over billions of years, that tiny divergence could mean the universe ages dramatically differently than we thought. The real puzzle: both methods are fundamentally sound. Cepheids have been the gold standard for cosmic distance measurements since Henrietta Leavitt discovered their rhythmic brightness patterns over a century ago. Meanwhile, the CMB data from missions like Planck is so precise it's often called the baby picture of the universe. So if both approaches are rock solid, why do they clash? Some theorists suggest hidden physics might be at play, perhaps dark energy, the mysterious force accelerating cosmic expansion, isn't constant as we assumed but evolves over time. Others wonder if unknown particles or exotic forms of matter are subtly tweaking the universe's expansion rate. There's even wilder speculation. Could our corner of the cosmos sit in a peculiar underdense region, like a bubble where matter is sparser than average, throwing off our local measurements. The unsettling truth is that every proposed solution forces us to question something fundamental, whether it's our understanding of gravity, the behavior of dark energy, or the very uniformity of the universe. This first anomaly isn't just a technical hiccup, it's a fork in the road for cosmology. If the local and cosmic measurements can't be reconciled, we might need to rewrite parts of the standard model that have guided astronomy for decades. And with each new observation, the tension only grows sharper, leaving scientists scrambling for answers in the most unexpected places. The very stars we use as cosmic measuring sticks might be throwing off our calculations more than we realize. Those Cepheid variables, the rhythmic pulsating stars that act as lighthouses for measuring galactic distances, aren't as straightforward as they seem. For over a century, astronomers have relied on their predictable brightness cycles to gauge how far away galaxies are, and by extension, how fast the universe is expanding. But here's the catch. Tiny uncertainties in calibrating these celestial yardsticks can snowball into massive disagreements in the Hubble constant. A slight misstep in measuring a Cepheid's true brightness or distance could skew the entire cosmic expansion rate by a staggering margin. Take the latest research from the James Webb Space Telescope, for example. When it turned its infrared gaze on Cepheids in galaxies like NGC 4258, it uncovered something startling. Dust swirling around these stars, previously thought to have only a minor effect, turns out to scatter and absorb their light in ways that subtly distort distance measurements. Even a 5% miscalibration in a single Cepheid's brightness might ripple outward, inflating or deflating the Hubble constant by kilometers per second per megaparsec. That might not sound like much, but in a field where precision is everything, it's enough to send theorists back to the drawing board. The controversy deepens when you consider alternative calibration methods. Some astronomers argue that relying solely on Cepheids introduces hidden biases, especially when comparing nearby stars to those in distant galaxies. A study published just last year proposed using tip of the red giant branch stars, cooler, more stable giants whose brightness peaks at a predictable level, as a cross-check. Surprisingly, when they mapped distances using these stars instead of Cepheids, the Hubble constant shifted closer to the slower value derived from the cosmic microwave background. This isn't just academic nitpicking, it suggests our entire cosmic distance ladder might have a wobbly rung. Then there's the question of metallicity, the amount of heavy elements in a Cepheid's atmosphere. Stars richer in metals like iron pulsate slightly differently than their metal-poor counterparts, a subtlety that wasn't fully accounted for in earlier models. Teams using the Gaia spacecraft's ultra-precise parallax measurements recently found that metal-rich Cepheids in our galaxy appear dimmer than expected, skewing distance estimates for their counterparts in other galaxies. If we've been misjudging these stars' true luminosity across cosmic time, it could explain why local measurements of the Hubble constant clash so violently with those from the early universe. What's at stake here isn't just a technical adjustment, it's the integrity of our cosmic yardsticks. If Cepheids aren't the flawless distance markers we believe them to be, every galaxy's position on our maps might need revisiting. Some researchers are now advocating for a radical shift, abandoning traditional Cepheid calibrations altogether in favor of entirely new methods, like gravitational wave sirens from colliding neutron stars. These violent cosmic crashes emit ripples in spacetime with a brightness so predictable they could serve as universal standard candles, bypassing the pitfalls of starlight altogether. But until we have enough of these events to build a robust dataset, the astronomy community remains locked in a high-stakes debate, one where the answer might rewrite not just the Hubble constant, but how we measure the universe itself. The universe loves throwing curveballs, and red giant stars might be the latest pitch to leave cosmologists swinging. While Cepheid variables have long been astronomy's go-to distance markers, tip of the red, giant branch stars TRGB for short, offer what should be a cleaner alternative. These aging stars reach a predictable peak brightness when they ignite helium in their cores, creating what astronomers call the tip of their evolutionary path. Unlike pulsating Cepheids, whose brightness fluctuates, TRGB stars hit this luminosity ceiling and stay there, theoretically making them more reliable cosmic yardsticks. But when teams started using them to measure the Hubble constant, the results didn't just differ slightly from Cepheid-based calculations. They landed much closer to the slower expansion rate seen in the cosmic microwave background. This creates a bizarre cosmic tug-of-war. In galaxy after galaxy, TRGB measurements consistently suggest the universe is expanding about 6% slower than Cepheids indicate. At first glance, that might not sound earth-shattering, but in cosmology, even a 1% discrepancy can upend theories. The real shock came when researchers compared both methods in the same galaxy. Take NGC 1566, a spiral galaxy 10 million light-years away. When measured with Cepheids, its distance suggested a faster Hubble constant. When the same galaxy's TRGB stars were analyzed, the expansion rate dropped significantly. It's like using two different tape measures on the same object and getting conflicting numbers, except this tape measure spans the cosmos. What makes this anomaly so perplexing is that both methods should be bulletproof. TRGB stars avoid many of Cepheids' pitfalls. They're less affected by dust, their brightness doesn't depend on pulsation periods, and they're found in all galaxy types. Yet when the Hubble Space Telescope and ground-based observatories like the Magellan telescopes cross-checked these stars, discrepancies emerged in their calibration. Some teams argue that even TRGB measurements have subtle biases, particularly in how we define the exact moment a star reaches its tip brightness. Others suggest the star's metallic environments might skew results, as metal-rich red giants could behave differently than their metal-poor cousins. The plot thickens when you consider how these stars interact with their galactic neighborhoods. Recent studies show red giants in crowded star clusters might experience mass loss, shedding outer layers that slightly alter their apparent brightness. Meanwhile, in metal-poor dwarf galaxies, TRGB stars shine more cleanly but are harder to isolate from background stars. This means depending on where astronomers look, TRGB stars could be whispering different versions of cosmic truth. The tension has grown so intense that some researchers now propose a radical idea. Maybe both methods are correct in their own contexts, hinting at a universe where expansion rates vary regionally, a concept that would overturn cosmology's assumption of large-scale uniformity. As teams race to resolve this clash, new instruments like the Nancy Grace Roman Space Telescope promise sharper views of red giants across millions of galaxies. Until then, the TRGB anomaly remains a glaring reminder that even our best cosmic tools might be showing us only part of the picture, and that the universe's expansion could be far more nuanced than a single number can capture. Astronomers thought they had a workaround for the Cepheid controversy with tip of the red giant branch stars until this method started revealing its own set of contradictions. The TRGB technique hinges on a beautifully simple cosmic phenomenon. When a red giant star fuses helium in its core, it hits a brightness ceiling that's nearly identical across the universe, like a built-in cosmic light bulb with a fixed wattage. By spotting this telltale luminosity peak in distant galaxies, scientists can calculate distances with what should be unparalleled consistency. Yet when they plug these distances into Hubble constant calculations, the resulting expansion rates don't just clash with Cepheid-based numbers, they also don't quite match the slower values from the cosmic microwave background. Suddenly, we're not dealing with a two-way tug-of-war, but a three-way standoff where every measurement stubbornly refuses to converge. What makes the TRGB tension especially puzzling is its timing. Unlike Cepheids, which pulsate unpredictably, or the CMB, which captures the universe's infancy, red giants represent a middle ground, they're middle-aged stars reflecting the universe's expansion over the last several billion years. If the Hubble constant were truly constant, their measurements should bridge the gap between local Cepheid readings and primordial CMB data. Instead, they land somewhere in between, as if the universe's expansion hit a mysterious speed bump during cosmic adolescence. A 2022 study of 12 galaxies using the Hubble Space Telescope found TRGB-derived expansion rates splitting the difference faster than the CMB's value, but slower than Cepheids, leaving theorists scrambling to explain why the universe's expansion might appear to decelerate over time. One provocative explanation lies in the way we observe these stars. While TRGB brightness should be universal, factors like galaxy environments and stellar populations introduce subtle wrinkles. For instance, red giants in dense galactic cores might appear brighter due to extra light from neighboring stars, while those in isolated dwarf galaxies could be dimmed by intervening dust. Even the way astronomers define the exact tip of the red giant branch isn't standardized. Some teams use statistical algorithms to pinpoint it, while others rely on visual cues, leading to minor but consequential variations. The Cepheid collaboration, famous for its Cepheid-based Hubble Constant Measurements, recently argued that certain TRGB calibration techniques inadvertently borrow assumptions from Cepheid physics, potentially skewing results. Meanwhile, independent groups using pure TRGB methods continue to report values that drift toward the CMB's slower rate, deepening the divide. The plot twist. TRGB stars might actually be revealing a cosmic reality we've been blind to, that the Hubble constant isn't so constant after all. Some models suggest dark energy could be evolving, its repulsive force weakening over time, which would cause the universe's expansion to slow imperceptibly between the CMB era and today. Others speculate that unknown particles like sterile neutrinos might have briefly altered the expansion rate during the universe's middle age, leaving a fingerprint only detectable through red giants. There's even a fringe hypothesis that our galaxy sits in a rare cosmic void, distorting nearby measurements across all methods. As the James Webb Space Telescope begins scrutinizing TRGB stars with unprecedented infrared clarity, astronomers hope to cut through the noise. Early results from Webb's observations of galaxy NGC 6822 showed tantalizing hints that dust corrections for red giants might be larger than previously thought, potentially nudging TRGB values closer to Cepheid-based rates. But until these findings are replicated across hundreds of galaxies, the TRGB anomaly remains a stubborn hurdle, reminding us that the universe's expansion rate might not be a single number after all, but a story still being written. Deep in the swirling arms of distant galaxies, nature provides an unlikely measuring tape: cosmic water masers. These aren't lasers but microwave beams emitted by water molecules orbiting supermassive black holes, creating pinpoints of radio light so precise they can map a galaxy's structure down to the milliarcsecond. For astronomers, masers are like GPS beacons in the void, offering what should be the gold standard for distance measurements. By tracking how these microwaves shift as their host galaxies move away from us, scientists can derive the Hubble constant with minimal uncertainty. But here's the catch: when maser-based distances are compared to other methods, they don't just disagree, they pick sides in the Hubble tension, aligning eerily with the slower expansion rate from the cosmic microwave background while clashing with Cepheid and TRGB measurements. Take the galaxy NGC 4258, home to one of the most precisely measured maser systems. After a decade of observations with radio telescopes like the Very Long Baseline Array, researchers pinned its distance at 22 million light-years with an uncertainty of just 3%, a staggering feat in cosmic cartography. Plugging this into Hubble constant calculations gave a value closer to 67 km per second per megaparsec, mirroring the CMB's estimate. Yet when the same galaxy's Cepheids were measured, they suggested a faster rate of 73. This isn't just a minor discrepancy. It implies that one of these methods is fundamentally misreading the universe's expansion, and the maser's radio clear signal leaves little room for error. The strangest part, masers sidestep many pitfalls plaguing other techniques. Unlike Cepheids, they're unaffected by interstellar dust that dims starlight, and unlike TRGB stars, their emissions don't depend on stellar evolution models. Their precision comes from geometry. By mapping the maser spot's motions in a disk around a black hole, astronomers can triangulate distances using pure trigonometry, no cosmic ladder required. So why would these impeccable measurements diverge from local universe observations? Some theorists point to the environments hosting masers. These water molecules thrive in dense, turbulent regions near black holes, where gravitational warping or unseen gas might subtly alter their signals. Others propose that masers, often found in older, metal-rich galaxies, trace a different cosmic epoch than the younger stars used in Cepheid and TRGB studies, hinting that the Hubble constant might not be uniform across time or space. A 2019 study of the maser galaxy UGC 3789 added fuel to the fire. Its maser-derived Hubble constant matched the CMB's value so precisely that statisticians ruled the odds of a fluke at less than 1 in 100,000. Yet just 2 years later, updated Cepheid measurements from the same region contradicted it outright, leaving the astronomy community split. One camp argues masers could be systematically underestimating distances due to unmodeled disk inclinations or maser spot instability. Another suggests Cepheids might be contaminated by unrecognized stellar companions or metallicity effects. But with each new maser galaxy mapped, only about a dozen are precise enough for Hubble calculations. The pattern holds. They persistently lean toward a slower, CMB-like universe. This anomaly cuts to the heart of the Hubble tension. If masers are correct, our local measurements must be missing something critical, perhaps an unseen population of Cepheids or a flaw in how we calibrate cosmic yardsticks. If they're wrong, it means even our most pristine distance markers harbor hidden biases. Either scenario forces a reckoning with how we measure the cosmos, proving that in the quest to pin down the universe's expansion, even the clearest signals can lead us into deeper mystery. When a dying star explodes as a Type Ia supernova, it unleashes a flash of light so uniform that astronomers call these events standard candles, cosmic beacons whose predictable brightness lets us measure vast intergalactic distances. For decades, they've been our most reliable tool for probing the universe's expansion, with their consistent peak luminosity serving as a ruler against the darkness. Yet this reliability is now under scrutiny because when scientists calculate the Hubble constant using these supernova, the numbers keep drifting into the same contentious divide plaguing other methods. Some Type Ia measurements align with the faster local universe rate, while others creep unsettlingly close to the slower cosmic microwave background value. It's as if the universe handed us a stopwatch that ticks at different speeds depending on where we look. The inconsistency is baffling because Type Ia supernova should be nature's most impartial distance markers. They occur when white dwarf stars' stellar embers roughly the size of Earth siphon too much mass from a companion and detonate in a runaway thermonuclear blast. Since these explosions always happen at the same critical mass threshold, their luminosity barely varies, or so we thought. But recent surveys like the Dark Energy Survey and Pantheon Plus have uncovered subtle anomalies in their light curves, patterns of brightening and fading that suggest some supernova might be intrinsically dimmer or brighter than expected. A 2023 study of over 1,500 supernova found that those in younger, metal-rich galaxies appear systematically brighter than their older counterparts in metal-poor galaxies, enough to skew distance estimates by up to 5%. This supernova evolution hypothesis throws a wrench into decades of cosmological assumptions. If supernova brightness depends on the chemical makeup of their galactic environment, then using them as uniform standard candles becomes perilous. Imagine trying to measure a marathon with a stretchy tape measure. The more metal-rich the neighborhood, the more the cosmic ruler might expand or contract. Some researchers argue this could explain why supernova-derived Hubble constants sometimes split the difference between Cepheid and CMB values. Their light carries hidden imprints of the universe's changing composition over billions of years. The plot thickens with the discovery of peculiar type Ia subtypes. Around 1 in 5 of these supernovae exhibit slower light curve declines or unusual spectral lines, hinting at different explosion mechanisms, perhaps merging white dwarfs instead of single stars stealing mass. The Zwicky Transient Facility's real-time sky scans have caught dozens of these oddballs, and when their distances are calculated, they frequently pull the Hubble constant in unexpected directions. Even more provocative are studies suggesting that dust in host galaxies might not dim supernova light uniformly. Certain wavelengths could be selectively absorbed, tricking our measurements. What makes this anomaly so pivotal is that type Ia supernova were the very data that first revealed dark energy's existence in the late 1990s. If their behavior isn't as standardized as we believed, it casts doubt not just on the Hubble constant but on our entire understanding of cosmic acceleration. Teams are now racing to recalibrate supernova models using next-gen telescopes like the Vera Rubin Observatory, which will catalog millions of these explosions. Until then, the supernova Ia puzzle remains a stark reminder that even the universe's most reliable fireworks might be flickering in ways we're only beginning to decipher. Einstein's theory of relativity gave us an unexpected cosmic stopwatch: gravitationally lensed quasars. These distant, brilliant objects shine light that gets warped and magnified as it passes through massive galaxies, creating multiple images of the same quasar flickering like echoes across space. But here's the twist: because each light path bends around different parts of the lensing galaxy, their arrivals on Earth get staggered by days, weeks, or even years. By meticulously tracking these delays, astronomers can triangulate the universe's expansion rate with a method utterly independent of Cepheids or the cosmic microwave background. Yet when they crunch the numbers, the Hubble constant that emerges refuses to pick a side, hovering stubbornly between the faster local measurements and the slower CMB value, as if the universe itself can't decide how fast it's growing. The precision of this technique hinges on celestial geometry at its most elegant. Imagine a quasar 5 billion light-years away, its light bent by a galaxy halfway between us and it. The light taking the longer path around the galaxy's outskirts might arrive 3 weeks later than the light that skimmed closer to the galaxy's core. By measuring this delay alongside the lensing galaxy's mass distribution mapped via Hubble Space Telescope images, scientists can calculate the absolute distances involved, bypassing the cosmic distance ladder entirely. The H0 collaboration study of 6 lensed quasars delivered a Hubble constant around 73 km per second per megaparsec, eerily matching Cepheid-based values. But when the SHARP team analyzed another set of lenses, their results dipped toward 69, leaning closer to the CMB 67. This split isn't random error. It suggests an unsettling pattern where lensing systems in certain cosmic environments skew faster or slower. What's really baffling is why these measurements can't break the deadlock. Gravitational lensing doesn't rely on stars' brightness or the universe's early conditions. It's pure space-time geometry. Yet subtle factors might be muddying the waters. The distribution of dark matter in lensing galaxies isn't perfectly smooth. Clumps and subhalos invisible to telescopes could subtly alter light paths, skewing time delay calculations. A 2021 simulation showed that just a 5% fluctuation in a lens's dark matter density might bias Hubble constant results by up to 3%. Then there's the lensing galaxy's peculiar motions. These massive structures aren't perfectly at rest in the expanding universe. Their local gravitational tugs could stretch or compress time delays like a funhouse mirror, mimicking a faster or slower cosmic expansion. The most provocative explanation, lensed quasars might be capturing a transitional epoch in the universe's expansion history. Most lie midway between the nearby Cepheids and the ancient CMB, probing a cosmic teenage phase where dark energy's influence was still ramping up. If dark energy's repulsive force wasn't constant but instead evolved over billions of years, lensing systems could be registering a moment when expansion began accelerating, leaving us with a Hubble constant that's neither fully local nor primordial. Supporting this, a 2023 analysis of 32 lenses found their expansion rates clustered midway between the dueling values, as if the universe itself hit a temporary speed bump. As new telescopes like the Vera Rubin Observatory prepare to discover thousands more lensed quasars, astronomers hope to untangle these contradictions. But for now, each flickering, time-delayed image serves as both a cosmic yardstick and a riddle, one that insists our map of the universe's expansion is missing something profound. Whether it's unseen dark matter, evolving dark energy, or a flaw in relativity itself, gravitational lenses are whispering secrets we've yet to fully decode. Galaxies hold a subtle visual fingerprint that could rewrite cosmic distance measurements, if only we could decode it consistently. Known as surface brightness fluctuations, this phenomenon exploits how galaxies look slightly grainy when observed through powerful telescopes. The effect arises because even the densest galaxies can't pack stars perfectly smoothly. Some regions appear brighter simply due to random clustering of stars. By quantifying this granularity, measuring how much the light flickers from pixel to pixel, astronomers can gauge a galaxy's distance, since farther galaxies appear smoother as their stellar clumps blend together. It's like judging how far away a forest is by observing whether individual tree leaves become indistinguishable. But when scientists apply this technique to calculate the Hubble constant, the results ricochet unpredictably between the faster local universe rate and the slower cosmic microwave background value, exposing yet another crack in our cosmic measurement toolkit. What makes this anomaly so perplexing is that surface brightness fluctuations avoid many pitfalls of other methods. Unlike Cepheids or supernova, they don't rely on identifying individual stars or explosions. They work best on elliptical galaxies where stars are too densely packed to resolve. The method also sidesteps dust-related errors, as it measures relative fluctuations rather than total brightness. Yet when teams applied it to galaxies like NGC 4515 and NGC 4373, their Hubble constant values swung wildly depending on subtle calibration choices. A 2020 study found that adjusting how star colors are accounted for could shift results by up to 5%, enough to flip the expansion rate from Cepheid aligned to CMB compatible overnight. The root of the discrepancy might lie in galaxies' hidden complexity. Elliptical galaxies, the prime targets for this method, aren't the uniform star fields we once assumed. Dark matter halos, globular clusters, and even rogue gas clouds can subtly alter surface brightness patterns in ways that mimic distance effects. Worse yet, the technique assumes all galaxies have similar stellar demographics, but if some ellipticals harbor unexpected populations of faint red dwarfs or bright giants, their graininess becomes misleading. The massive survey recently found that accounting for these hidden stellar populations in galaxy NGC 1407 pulled its surface brightness fluctuation distance 12% closer, a colossal adjustment in cosmic terms. Even the telescopes themselves might be skewing results. Surface brightness measurements require exquisitely uniform data, but variations in detector sensitivity or image processing algorithms can introduce artificial graininess. When the Hubble Space Telescope and ground-based observatories like the Subaru telescope measured the same galaxies, their fluctuation analyses sometimes differed by margins larger than statistical error. Some teams now advocate combining this method with complementary techniques like the fundamental plane of elliptical galaxies, a three-way relationship between size, brightness, and velocity dispersion. But when blended datasets still refuse to converge on a single Hubble constant, it suggests the problem isn't just technical, it's cosmological. This anomaly forces a humbling realization. Even the most elegant cosmic rulers may be warped by the universe's messy realities. As next-generation telescopes like the Nancy Grace Roman Space Telescope prepare to map surface brightness fluctuations across thousands of galaxies, astronomers hope to finally separate cosmic signal from stellar noise. Until then, these flickering galactic patterns remain both a promise and a warning, a reminder that in our quest to measure the expanding universe, even the subtlest details can tilt the cosmic scale. Galaxies aren't just collections of stars, they're cosmic whirlpools, spinning with a rhythm that could reveal the universe's expansion if we can read their dance correctly. The Tully-Fisher relation, a cornerstone of astrophysics since the 1970s, connects a galaxy's rotation speed to its brightness. The faster it spins, the more luminous it tends to be. This elegant correlation turns spiral galaxies into natural speedometers, letting astronomers estimate their distances by measuring how swiftly their stars and gas swirl. But when these measurements get plugged into Hubble constant calculations, they don't always play nice with other methods. Sometimes they align with the faster local universe rate. Other times, they drift uncomfortably close to the slower cosmic microwave background value, as if galaxies themselves can't agree on how fast space is stretching. The trouble starts with how we measure galactic rotation. Using radio telescopes, astronomers track the Doppler shifts of hydrogen gas clouds whipping around a galaxy's outskirts, plotting their speeds against the galaxy's total luminosity. In theory, this should give a straightforward distance estimate, except galaxies are messier than textbooks suggest. Dark matter, which outweighs visible stars 10 to 1, tugs on outer gas clouds, subtly altering rotation curves in ways that vary from galaxy to galaxy. A 2021 study of 300 spirals found that galaxies with massive dark matter halos rotated faster than their luminosity predicted, skewing Tully-Fisher distances by up to 15%. Even more confounding, the relation behaves differently depending on a galaxy's shape. Late-type spirals with loose arms follow the classic Tully-Fisher trend neatly, while barred spirals, those with central star-forming rods, often spin faster than their brightness should allow, throwing off calculations. Calibration adds another layer of mystery. To anchor the Tully-Fisher relation, astronomers need galaxies with independently known distances, usually from Cepheid variables. But this creates a circular dependency if Cepheids themselves are miscalibrated. As some anomalies suggest, Tully-Fisher inherits those errors. The tension became impossible to ignore when the Extragalactic Distance Database released its latest analysis, showing Tully-Fisher-based Hubble constants bifurcating along galactic environment lines. Isolated field galaxies leaned toward faster expansion rates, while those in dense clusters nudged closer to the CMB's slower value. This split hints that local gravitational interactions, tides from neighboring galaxies, or cluster-scale dark matter might be warping rotation speeds in ways we don't yet model. The most startling twist came when teams tried updating the relation with infrared data. Dust obscures up to half a spiral galaxy's starlight, but infrared telescopes like Spitzer peer through that veil to measure true luminosities. Yet when scientists recalculated distances using these cleaner infrared fluxes, the Hubble constant values didn't converge, they scattered wider. A 2019 paper argued that older, metal-rich galaxies emit more infrared light relative to their mass, mimicking the signal of slower rotation. Meanwhile, gas-rich dwarfs with vigorous star formation can appear anomalously bright in certain infrared bands, distorting their Tully-Fisher placement. It's as if every correction meant to simplify the relation only reveals new complexities. What makes this anomaly so pivotal is that the Tully-Fisher method bypasses the traditional cosmic distance ladder. It doesn't rely on a chain of overlapping techniques. If it consistently agreed with itself, it could break the Hubble tension wide open. Instead, its inconsistencies suggest something deeper. Maybe the universe's expansion isn't just a single number but a tapestry of local variations woven together by forces we're only beginning to trace. Until we understand why galaxies spin and shine differently in different corners of the cosmos, their whispers about the Hubble constant will remain tantalizingly out of sync. Baryon acoustic oscillations are like cosmic fossils, imprints left behind from the universe's infancy, when it was a seething plasma of particles and light. These subtle ripples in the distribution of galaxies trace back to pressure waves that raced through the primordial soup, freezing into place when atoms first formed. Today, they serve as a cosmic ruler with a known physical scale of about 500 million light-years. By measuring how stretched or compressed these patterns appear across the sky, astronomers can calculate how much the universe has expanded since those early moments and, by extension, pin down the Hubble constant. Yet when they do, the results don't just differ slightly from local measurements like Cepheids or supernova. They land almost squarely with the slower values from the cosmic microwave background, deepening the rift in our cosmic expansion saga. The precision of BAO measurements is staggering. Projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have mapped millions of galaxies, revealing these oscillation patterns with razor-sharp clarity. Because the original scale of these ripples is imprinted by well-understood physics from the universe's first 400,000 years, they should provide a foolproof yardstick. But when teams convert BAO data into a Hubble constant, the numbers consistently hover around 67 kilometers per second per megaparsec, matching the CMB's sluggish expansion rate and clashing violently with local estimates of 73. This isn't just a minor calibration quirk. It suggests that something fundamental may be missing from our models of how structure evolved across cosmic time. One explanation could lurk in the way dark energy interacts with large-scale structure. Most BAO analyzers assume dark energy has been a constant force, uniformly accelerating expansion. But if dark energy's strength waxed or waned over billions of years, it might have subtly altered how baryon waves stretched, making the universe appear to have expanded less than it actually did. A 2021 simulation showed that a hypothetical early dark energy phase, active before galaxies formed, could stretch BAO rulers just enough to lower the inferred Hubble constant by 5%, exactly the gap we're grappling with. Alternatively, neutrinos with unexpected masses might have skewed how matter clumped, leaving BAO measurements out of sync with local methods. The plot thickens when you consider redshift, the stretching of light wavelengths as the universe expands. BAO surveys typically split galaxies into slices of different redshifts to probe expansion at various cosmic epochs. Intriguingly, some studies find the Hubble constant creeping upward in more recent slices, as if the universe's expansion hit a speed bump a few billion years ago. This could mean BAO isn't wrong, it's capturing a transitional era when dark energy's grip on the cosmos tightened. Yet even this nuanced view struggles to explain why BAO and CMB values align so precisely while local techniques disagree so sharply. The stakes here go beyond academic debate. If BAO measurements are correct, then our local universe might be a statistical outlier, a bubble where expansion appears artificially fast due to unseen matter flows or gravitational quirks. But if BAO is missing some critical physics, it calls into question our entire understanding of how large-scale structure emerged from the Big Bang's aftermath. Upcoming galaxy surveys like Euclid and the Vera Rubin Observatory's LSST will map BAO patterns with unprecedented depth, hunting for cracks in the standard cosmological model. Until then, these frozen sound waves remain both a beacon of precision and a whisper of contradiction, a reminder that even the universe's oldest echoes might be telling us more than we've learned to hear. The Dark Energy Survey was supposed to cut through the Hubble tension like a scalpel. Instead, it revealed just how tangled the mystery truly is. For 6 years, this ambitious project scanned 1/8 of the night sky, cataloging hundreds of millions of galaxies and thousands of supernovae to map cosmic expansion with unprecedented breadth. The goal was simple: combine multiple independent probes, weak gravitational lensing, galaxy clustering, and type Ia supernova into a single, definitive measurement of the Hubble constant. But when scientists stitched these datasets together, they didn't get consensus. They got chaos. The same survey produced Hubble values that swung from 67 to 74 kilometers per second per megaparsec, depending on which combination of probes they used, as if the universe was deliberately obfuscating its own expansion rate. Take the supernova results alone. DES analyzed over 1,500 type Ia explosions, expecting them to mirror earlier findings that leaned toward faster local expansion. Yet when combined with the survey's galaxy distribution maps, the inferred Hubble constant unexpectedly dropped, aligning more closely with the slower cosmic microwave background value. The twist: this shift only appeared when accounting for subtle correlations between supernova brightness and their host galaxies' ages, a factor previous surveys had treated as negligible. Suddenly, a 5% adjustment in how we interpret stellar demographics could flip the entire expansion rate between conflicting paradigms. Weak lensing added another layer of contradiction. By measuring how massive structures warp the light of background galaxies, DES mapped the distribution of dark matter and thus the universe's growth over time. These observations suggested a Hubble constant around 68, neatly matching the CMB, but when researchers cross-checked with baryon acoustic oscillation data from the same galaxies, the numbers mysteriously crept upward. The culprit might lie in how galaxies bias dark matter maps. Younger, star-forming galaxies tend to cluster differently than older red galaxies, potentially skewing lensing measurements by up to 3%. This isn't just statistical noise. It implies that the tools we use to measure expansion are themselves sensitive to cosmic evolution in ways we're only beginning to grasp. The most provocative DES finding came from combining all 3 probes. In theory, this 3-pillar approach should cancel out individual methods' errors, delivering rock-solid results. Instead, the final composite Hubble constant landed squarely between the dueling CMB and local estimates, not as a compromise, but as a statistical impossibility under standard cosmology. A 2022 paper showed this middling value required either unseen systematic errors across all techniques or, more startlingly, a breakdown in our understanding of how dark energy influences structure formation. Some theorists now speculate that dark energy's repulsive force might vary across cosmic epochs, subtly tweaking each probe's perception of expansion. What makes the DES anomalies so unsettling isn't just the numbers, it's the realization that our most sophisticated surveys might be revealing a universe far more nuanced than a single Hubble constant can capture. As one team member put it, we built a machine to measure the universe's heartbeat, and it's showing us a arrhythmia. With future projects like the Vera Rubin Observatory preparing to magnify this approach tenfold, astronomers are bracing for even deeper contradictions, ones that could force us to redefine not just how fast the cosmos expands, but what's actually driving it apart. One of the most profound cracks in our understanding of cosmic expansion isn't just about conflicting measurements, it's about timing. When we peer back to the universe's infancy using the cosmic microwave background, the Hubble constant whispers a slower, more measured expansion rate. But when we look at the modern universe with tools like Cepheids and supernova, the number leaps upward as if the cosmos has been secretly pressing the accelerator. This early versus late universe mismatch isn't just a technical glitch, It's a cosmic paradox suggesting that either our measurements are fatally flawed, or the universe's expansion doesn't follow the rulebook we've written for it. The cosmic microwave background is like a fossilized echo of the Big Bang, capturing the universe's state just 380,000 years after its birth. By studying subtle temperature variations in this afterglow, scientists can extrapolate how fast space was stretching back then, and by extension, how fast it should be expanding today. The Planck satellite's meticulous maps point to a Hubble constant around 67 kilometers per second per megaparsec. But when astronomers measure the present-day universe using nearby supernova and Cepheid variables, the number spikes to 73. That 6% gap might sound trivial, but over cosmic time, it implies the universe has been expanding 8% faster than projected for billions of years. It's as if we've been tracking a train's speed based on its departure time, only to find it's inexplicably miles ahead of schedule. This temporal disconnect forces astronomers to confront two equally unsettling possibilities. Either something is systematically wrong with how we measure distances, perhaps Cepheids, supernova, or even the CMB itself harbor hidden calibration errors, or the universe's expansion rate isn't constant at all. The latter scenario would upend cosmology's bedrock assumption that dark energy's repulsive force has been steady since the dawn of time. If dark energy's strength has been creeping upward, it could explain why the modern universe seems to be rushing apart faster than its early conditions predicted. Some models suggest an early dark energy phase, a burst of extra repulsion in the universe's first few million years that subtly altered the CMB's expansion signature. Others propose that dark energy interacts with dark matter, gradually amplifying its push over eons. The most radical theories dare to question general relativity itself. Could gravity's grip weaken over cosmic distances or timescales, mimicking an acceleration that isn't truly there? Modified gravity models like modified Newtonian dynamics have long lurked at cosmology's fringes, but this Hubble tension gives them new teeth. Yet even these exotic ideas struggle to explain why local and early universe measurements diverge so cleanly along temporal lines. What makes this anomaly uniquely thorny is that both sets of measurements, early and late, are staggeringly precise. Planck's CMB data has margins of error under 1%, and supernova surveys like SH0ES boast similar confidence. This isn't a case of fuzzy data. It's a fundamental clash between two empirical pillars of modern cosmology. Upcoming missions like the Simons Observatory and CMB-S4 will scrutinize the CMB's polarization for clues, while the Vera Rubin Observatory's decade-long sky survey may reveal if local expansion rates vary across different cosmic neighborhoods. Until then, the early versus late universe mismatch stands as cosmology's most tantalizing riddle, a temporal tear in the fabric of our cosmic understanding that no amount of observational prowess has yet been able to stitch shut. Could the ghostly particles streaming through your body right now hold the key to the Hubble tension? Enter neutrinos, the universe's most elusive wanderers, so light and weakly interacting that trillions pass through you every second without a trace. These subatomic phantoms were long thought to be massless, but we now know they carry a whisper of weight, and that tiny mass might be warping cosmic expansion in ways we never anticipated. When physicists tweak neutrino properties in supercomputer simulations of the early universe, the resulting Hubble constant shifts perceptibly, as if these spectral particles are subtly tugging at the fabric of spacetime itself. The crux lies in how neutrinos sculpted the cosmos during its formative years. In the first second after the Big Bang, neutrinos outnumbered protons and electrons 10 billion to 1, forming a sea of ultra-fast particles that influenced how matter clumped together. Heavier neutrinos would have acted like cosmic dragsters, slowing down the formation of galaxies and galaxy clusters by dispersing energy across vast distances. Lighter ones would have zipped through the infant universe almost unimpeded, allowing structures to coalesce faster. This delicate balance leaves fingerprints in both the cosmic microwave background and the distribution of galaxies we see today, fingerprints that change depending on whether we assume neutrinos are feather-light or carry just a bit more heft. Current experiments suggest neutrinos have a combined mass of at least 0.06 electron volts, roughly a 10 millionth of an electron's weight. But here's where it gets wild. If that number creeps up to even 0.15 electron volts, early universe simulations start spitting out Hubble constants closer to the slower CMB value, while local measurements remain unaffected. This happens because neutrino mass alters the sound wave patterns frozen into the CMB, making the universe appear to have expanded more slowly than it actually did. The South Pole's Ice Cube Neutrino Observatory recently detected hints that high-energy neutrinos might interact more strongly with matter than predicted, a potential clue that their masses aren't distributed evenly among the three known types. The plot thickens when you consider sterile neutrinos, a hypothetical fourth flavor that doesn't interact via any known force except gravity. If these shadowy particles exist, they could have dominated the early universe's energy budget, temporarily putting the brakes on expansion before decaying into undetectable energy. A 2023 paper showed that sterile neutrinos with masses around 1 electron volt could reconcile the Planck CMB data with local supernova measurements, bridging the Hubble gap without invoking exotic dark energy behaviors. The catch: no experiment has definitively spotted these phantom particles yet. What makes the neutrino hypothesis so compelling is its elegance. It doesn't require overthrowing general relativity or inventing new cosmic forces. A slight adjustment to these ubiquitous particles' properties might explain why early and late universe measurements diverge, all while keeping our standard model of cosmology largely intact. But until next-generation experiments like the Deep Underground Neutrino experiment pin down their exact masses, these ethereal particles will remain both a tantalizing solution and a maddening enigma in the Hubble constant saga, silent architects of cosmic expansion hiding in plain sight. What if dark energy isn't just accelerating the universe's expansion, but doing so with a vengeance? Enter phantom dark energy, a hypothetical force so extreme it defies the conventional laws of cosmology. Unlike ordinary dark energy, which gently pushes galaxies apart at a steady pace, phantom dark energy grows stronger over time with an equation of state where W dips below -1. This isn't just a minor tweak, it's a cosmic wildcard that could stretch spacetime so violently that distant galaxies would eventually rip apart atom by atom in a Big Rip scenario. But before that apocalyptic finale, this phantom force might already be leaving fingerprints on the Hubble tension, subtly tweaking the universe's expansion history to bridge the gap between conflicting measurements. The math behind this idea is as haunting as its name implies. In cosmology, dark energy's equation of state, represented by W, describes how its energy density evolves as the universe expands. Ordinary dark energy, like Einstein's cosmological constant, has W equals -1, meaning its push remains uniform across space and time. But phantom dark energy's W plunges below that threshold, causing its repulsive force to amplify exponentially. Picture a car where pressing the accelerator doesn't just maintain speed, it makes the pedal sink deeper on its own, sending the vehicle hurtling faster with each passing second. If such a force existed in the early universe, it could have briefly turbocharged expansion just after the cosmic microwave background era, making the CMB's inferred Hubble constant appear deceptively low compared to today's runaway pace. Critically, this isn't just speculative math, it's a potential solution hiding in plain sight. A 2020 study showed that phantom dark energy with W around -1.1 could reconcile Planck's CMB data with local supernova observations, stretching the early universe's expansion just enough to align both sets of measurements. The kicker: This adjustment wouldn't require throwing out general relativity or inventing new particles, just allowing dark energy to behave more ferociously than we'd assumed. Support comes from unexpected corners. Some analyses of galaxy clusters and quasar distributions have found hints of W values creeping perilously close to the phantom zone, though still within margin of error. Yet phantom energy raises more questions than it answers. If the universe underwent a phantom-powered speed boost a few billion years ago, why don't we see sharper evidence in the fossil records of galaxy formation? And how could such a force avoid triggering vacuum decay, a catastrophic quantum event that would erase spacetime itself? Some theorists argue phantom energy might be an illusion, a mirage caused by our imperfect cosmic perspective. If we're trapped in a vast underdense region of the universe, the apparent acceleration beyond W equals -1 could simply be gravity's uneven tug distorting our measurements. Others propose it's not a single force but a signpost of multiple dark energy phases, where the universe has lurched through different expansion regimes like gears shifting in a cosmic transmission. As tantalizing as phantom dark energy is, it remains a last resort for many physicists, a cosmological Hail Mary that keeps the standard model intact at the cost of introducing apocalyptic physics. Until future probes like ESA's Euclid telescope or NASA, a Roman space telescope, map dark energy's equation of state with precision, this phantom will continue lurking at the edges of our equations, whispering that the universe's expansion might be far more volatile than we ever dared imagine. What if gravity itself is the cosmic wild card we've been missing? While most astronomers chase dark energy or measurement errors to solve the Hubble tension, a bold faction is questioning the very laws Einstein etched in stone. Modified Newtonian dynamics, MND for short, proposes that gravity doesn't fade with distance as Newton or Einstein predicted. Instead, it tugs harder in the faint outskirts of galaxies where stars orbit faster than standard physics allows. This tweak was originally crafted to explain galactic rotation without invoking dark matter, but its implications ripple all the way to the Hubble constant. If gravity's grip strengthens where we least expect it, the universe's expansion history could look dramatically different, potentially bridging the gap between conflicting measurements. The math behind these theories is as radical as it gets. Traditional cosmology relies on general relativity's elegant equations, where space-time curvature dictates how matter moves and how the cosmos expands. But MND introduces an acceleration threshold around 1/10 billionth of a g below which gravity switches to a stronger mode. Apply this to the large-scale structure of the universe and suddenly, galaxies don't just behave differently, the fabric of spacetime itself might stretch in unexpected ways. A 2021 simulation showed that MND, like gravity, could mimic an accelerated expansion without dark energy, potentially aligning early and late universe Hubble measurements by bending the rules of cosmic growth. Then there are the higher dimensional models where gravity leaks into unseen dimensions we can't perceive. Imagine our three-dimensional space as a slice of toast in a cosmic toaster. Gravity, unlike other forces, might seep into the extra dimensions like melted butter, weakening its apparent strength in our observable universe. If true, this could mean our measurements of galactic motions and cosmic expansion have been subtly skewed for decades. Some versions of string theory predict exactly this, with gravitational waves propagating differently than light across vast distances. When researchers at the Perimeter Institute tweaked their expansion models to include these leaks, the Hubble constant's stubborn discrepancies shrank by nearly half. But here's the catch: modified gravity theories demand sacrifices. To work, many must abandon cherished principles like Lorentz invariance, the idea that physics works the same no matter your speed or direction. Others struggle to explain why galaxy clusters still seem to need dark matter's extra mass, or why gravitational waves from neutron-star mergers arrive in lockstep with light. The Cassini spacecraft's precision measurements of Saturn's orbit also put strict limits on how much gravity can deviate from Einstein's predictions within our solar system. Yet proponents argue these wrinkles don't kill the theories. They just confine their effects to cosmic scales where the Hubble tension lives. What makes these ideas so electrifying isn't just their potential to solve one anomaly, it's their audacity to rewrite physics itself. While most cosmologists tinker with dark energy or calibration errors, modified gravity throws a grenade into the equation, forcing us to ask, what if our most fundamental assumption about the cosmos, the way it bends and stretches, is the very thing we've gotten wrong? Until future probes like LISA or the Einstein telescope map gravity's behavior across the universe with unprecedented precision, these theories will remain both the most thrilling and polarizing contenders in the Hubble constant debate, proof that sometimes to measure the cosmos, you first have to unlearn its rules. Imagine if the entire cosmic neighborhood around us, our galactic backyard, was an anomaly. The Hubble bubble hypothesis dares to suggest exactly that. Earth and the Milky Way might reside inside a vast underdense region of space, a cosmic void where matter is spread thinner than in the surrounding universe. If true, this local bubble would distort nearby measurements of the Hubble constant, making galaxies appear to rush away faster than they actually are. It's like living in a valley and trying to judge the steepness of a mountain range beyond. Your perspective from below skews the true scale. This controversial idea gained traction because it offers an elegant way to split the difference in the Hubble tension. When we measure expansion using nearby supernova and Cepheid variables, we're sampling light that's traveled mostly through this hypothetical bubble. If the bubble's lower matter density weakens gravity's pull locally, galaxies here would seem to accelerate outward faster, inflating the Hubble constant. Meanwhile, measurements like the cosmic microwave background or baryon acoustic oscillations, which probe the universe's average density over vast scales, would remain unaffected, preserving their slower expansion rate. A 2018 study calculated that an underdense region spanning about 250 million light-years could explain nearly half of the discrepancy between local and early universe measurements. But the Hubble bubble faces fierce skepticism. For starters, such a void would need to be improbably large, far exceeding the scale of known cosmic structures like the Boötes void. The Milky Way's motion through space also contradicts the idea. If we were truly in a vast underdensity, our galaxy's peculiar velocity should show a telltale dipole pattern as we drift toward denser regions, but current observations reveal no such signal. More damningly, the bubble's existence would clash with the cosmological principle, the bedrock assumption that the universe looks roughly the same everywhere on large scales. If we're sitting in a special low-density pocket, it undermines centuries of astronomy built on cosmic uniformity. Yet the hypothesis refuses to die, fueled by quirks in recent data. The KBC void, named after astronomers Keenan, Barger, and Cowie, is a real, if smaller, underdense region centered on the Milky Way, spanning about 2 billion light-years. Its discovery hints that while we may not live in a Hubble bubble of the required scale, local density variations could still be nudging our measurements off kilter. Some theorists argue that even subtler inhomogeneities, thread-like cosmic filaments or sheet-like walls of galaxies, might collectively mimic a bubble's effect without violating the cosmological principle. Others propose that dark matter isn't distributed as smoothly as models assume, creating invisible pockets of weaker gravity that masquerade as underdensities. The debate boils down to a philosophical clash. Is the Hubble tension a sign that we're missing fundamental physics, or just victims of a cosmic optical illusion? Upcoming galaxy surveys like those from the Vera Rubin Observatory could settle the matter by mapping the local universe's density with unprecedented resolution. Until then, the Hubble bubble remains a tantalizing, What if, a reminder that sometimes the hardest thing to measure is your own place in the cosmos. At the heart of the Hubble constant crisis lies a question that keeps cosmologists awake at night. Are we staring at revolutionary physics or just fooling ourselves with hidden measurement flaws? The systematic errors debate cuts to the core of scientific humility, forcing astronomers to confront whether their tools are betraying them. On one side, teams like SH0 Supernova and H0 for the equation of state argue their Cepheid and Supernova measurements are airtight, with cross-checks reducing uncertainties to a mere 1.9%. But skeptics point to subtle gremlins that could lurk in the data. Maybe Cepheid brightness measurements are skewed by undiscovered binary star companions, or perhaps supernova light curves aren't as uniform across galaxies as we assumed. The controversy intensified when independent groups began dissecting each method's error budgets. Take the cosmic distance ladder, the step-by-step process linking nearby Cepheids to distant supernova. A 2023 reanalysis by the Pantheon Plus team found that tiny calibration shifts in just 3 anchor galaxies could tilt the Hubble constant by over 1 km per second per megaparsec. Even more unsettling, the Hubble Space Telescope's own optics might introduce subtle distortions. When scientists compared Cepheid distances measured by Hubble with those from Gaia's ultra-precise parallax data, they found discrepancies large enough to nudge the expansion rate up or down by 2%. That might sound negligible, but in this high-stakes game, it's the difference between confirming new physics or admitting we've been misreading our instruments. Then there's the cosmic microwave background's own potential blind spots. Planck's pristine maps of the early universe assume perfect knowledge of foreground effects. Dust in our galaxy, emissions from galaxy clusters that could muddy the CMB signal. A team at Cambridge recently showed that misestimating galactic dust polarization by just 0.1% might bias the inferred Hubble constant by a full kilometer per second. Similar debates rage over Barrian acoustic oscillations. Do galaxies trace the true underlying dark matter distribution, or do their peculiar motions introduce fingers of God distortions that throw off distance measurements? The DAISY survey's latest data suggests the latter effect could be 3 times larger than modeled, potentially resolving part of the tension without invoking exotic physics. What makes this debate so thorny is that both camps have compelling evidence. Proponents of new physics highlight how multiple independent methods lensed quasars, water masers, even the tip of the red giant branch, keep splitting into fast and slow camps regardless of technique. But error hunters counter that shared calibration sources or analysis pipelines might bake the same biases into different methods. The James Webb Space Telescope was supposed to settle things by cutting through dust-obscuring Cepheids, but its first results only deepened the divide. Some galaxy Cepheids appeared brighter than Hubble measured, others dimmer. The most provocative twist comes from machine learning. When AI systems like the cosmological neural network analyze raw data without human assumptions, they sometimes derive Hubble constants that split the difference between CMB and local values, hinting that both camps might be partly right and partly wrong. As error budgets shrink with better instruments, the anomalies only grow more persistent, leaving us at a crossroads. Either we're missing something foundational about how the universe expands, or we're collectively overlooking a systematic gremlin so subtle it's fooled every telescope we've built. In this high-stakes game of cosmic clue, the culprit could be hidden in the instruments, the data, or the very laws of nature themselves. The James Webb Space Telescope was supposed to be the great arbiter of the Hubble tension, a next-generation observatory powerful enough to cut through decades of debate with its razor-sharp infrared vision. Yet its early findings have done something far more intriguing than settling the argument. They've thrown gasoline on the fire. When JWST trained its golden mirrors on galaxies like NGC 4258 and NGC 1566, home to both Cepheid variables and tip of the red giant branch stars, the results didn't just confirm one camp's measurements, they split the difference in ways nobody predicted. Some Cepheids appeared brighter than Hubble's old readings suggested, nudging the Hubble constant downward toward the cosmic microwave background's slower expansion rate. Others stubbornly matched prior values, preserving the tension instead of resolving it. It's as if the universe handed JWST a riddle wrapped in an enigma and said, "Good luck." What makes these discrepancies so electrifying is the telescope's unmatched precision. Unlike Hubble, which struggled with dust-obscured Cepheids in crowded galactic cores, JWST infrared capabilities pierce through cosmic cobwebs to measure stellar brightness with less than 1% uncertainty. Its first target should have been slam dunks, carefully selected galaxies where both Cepheids and TRGB stars coexist, allowing direct cross-comparison. Yet when two separate teams analyzed the same JWST data, one group reported Cepheid distances aligning with a faster Hubble constant, while the other, using TRGB stars from the same images, found values leaning toward the slower CMB rate. The difference came down to microscopic choices in how stellar brightness was calibrated, proving that even with perfect data, hidden assumptions can tilt the cosmic scale. One startling revelation involves Cepheids' infrared excess, a faint glow of warm dust surrounding these pulsating stars that previous telescopes couldn't detect. JWST spectra show this dust contributes up to 10% extra light in certain wavelengths, meaning Hubble might have overestimated some Cepheids' intrinsic brightness. Correct for this, and their distances stretch slightly farther, lowering the inferred expansion rate. But here's the twist: this adjustment only works for metal-rich Cepheids in galaxies like our Milky Way. Metal-poor Cepheids in dwarf galaxies show no such excess, preserving their faster Hubble constant values. This duality suggests we're not dealing with a single cosmic expansion rate, but a spectrum influenced by galactic chemistry, a nuance that could redefine how we build the cosmic distance ladder. Meanwhile, JWST scrutiny of TRGB stars has unearthed its own surprises. These red giants, long considered more reliable than Cepheids because their luminosity depends on core physics rather than pulsation, now appear susceptible to environmental quirks. In galaxy NGC 1566, JWST spotted TRGB stars nestled in dense star-forming regions, their light subtly contaminated by neighboring hot young stars. Filter out this blue leakage, and their brightness calibrations shift enough to pull the Hubble constant down by 2%. Yet in quieter galaxies like NGC 1365, TRGB measurements held firm, aligning with prior values. The implication is uncomfortable. Even our most trusted cosmic yardsticks might be sensitive to their stellar neighborhoods in ways we're only beginning to map. The most tantalizing and unsettling JWST result comes from galaxy NGC 5584. Here, the telescope captured both Cepheids and a rare type Ia supernova in the same frame, offering a direct test of the distance ladder's consistency. The Cepheid-derived distance suggested a Hubble constant of 72, but the supernova's brightness implied 74. A 2-unit gap might seem trivial, but statistically, it's a 5 sigma discrepancy, a near-impossible fluke if our models are correct. Theorists are now scrambling to explain how two gold standard distance markers in the same galaxy could disagree so violently. Some propose that supernovas' luminosities vary with their progenitor stars' rotation speeds, a factor never before considered. Others suggest Cepheids in metal-rich environments like NGC 5584 pulsate differently due to internal gravity waves. JWST's greatest contribution to the Hubble tension might ultimately be this. It's shown us that the problem isn't just about measurement errors or new physics, it's about context. The universe's expansion rate might not be a single number but a tapestry woven from local conditions, stellar chemistries, and hidden variables we're only now discerning. As the telescope turns its gaze toward more galaxies, each dataset becomes both a clue and a complication. proving that even with the most advanced tools ever built, the cosmos refuses to surrender its secrets easily. Quasars should be the ultimate cosmic yardsticks, blazing beacons so bright they outshine entire galaxies, visible from the edge of the observable universe. These supermassive black holes, devouring matter and firing jets of radiation, have long been tapped as distance markers, their light stretched by the universe's expansion. Yet when astronomers use them to calculate the Hubble constant, the numbers veer wildly off script, sometimes aligning with local measurements, other times mirroring the cosmic microwave background, and occasionally landing in uncharted territory. The quasar distance scale problem isn't just another anomaly. It's a full-blown rebellion against our cosmic rulebook, revealing that even the universe's brightest objects might be playing tricks on us. The traditional approach relies on quasars' ultraviolet and X-ray emissions. As material spirals into the black hole's accretion disk, it heats up, producing ultraviolet light that interacts with nearby gas clouds, creating a predictable echo in X-rays. By measuring the time delay between these two signals, a technique called reverberation mapping, scientists can estimate the quasar's true luminosity and thus its distance. In theory, it's elegant. The longer the delay, the larger the gas cloud and the brighter the quasar must be. But in practice, the method keeps spitting out Hubble constants that zigzag across the board. A 2020 study of 70 quasars found expansion rates ranging from 65 to 75 kilometers per second per megaparsec, as if each quasar were anchored to a different version of the cosmos. Part of the chaos stems from quasars themselves. Unlike standardized candles like supernova, no two quasars are identical. Their accretion disks warp and flicker like cosmic funhouse mirrors, with some spewing jets that contaminate their ultraviolet signals, while others hide behind thick dust curtains that distort X-ray echoes. The Sloan Digital Sky Survey's quasar catalog reveals an even stranger wrinkle. The brightest quasars seem to follow one Hubble constant, while fainter ones skew toward another. This quasar brightness dichotomy suggests we might be dealing with multiple populations, some obeying local expansion rates, others echoing the early universe's slower pace. The plot thickens when quasars are compared to other distance markers in the same galaxies. In NGC 267, a quasar's reverberation mapping suggested a Hubble constant of 73, perfectly matching the galaxy's Cepheid variables. Yet in NGC 376, another quasar's measurement plunged to 67, aligning with the cosmic microwave background. The discrepancy can't be blamed on cosmic variance alone. These galaxies lie at similar distances. Some theorists argue that quasars' black hole masses critical for reverberation calculations might be systematically misestimated due to unmodeled disk winds or magnetic fields. Others propose that X-ray echoes don't always trace the same physical structures across different quasars, introducing hidden biases. The most provocative clue comes from quasars lensed by foreground galaxies. These cosmic mirages produce multiple images of the same quasar, with time delays that should provide independent distance checks. Yet when teams like H0LICW analyzed these systems, they found quasar-derived Hubble constants clustering midway between local and CMB values, as if lensed quasars are capturing an expansion rate that's neither here nor there, but somewhere in the universe's murky middle age. This Goldilocks zone of disagreement hints that quasars might be sensitive to an epoch when dark energy's grip on the cosmos was still tightening, leaving behind a fossil record of transitional expansion. As next-generation telescopes like the Vera Rubin Observatory prepare to map millions of quasars, astronomers are bracing for even deeper contradictions. These enigmatic objects, once hailed as the universe's most reliable lighthouses, now illuminate something far more unsettling, that our cosmic maps might be fractured along invisible fault lines, with each measurement method peering through a different crack in reality's facade. Whether the culprit is quasars' unruly physics, hidden cosmic variables, or something beyond our current theories, one thing is clear: the farther we look into the void, the less it agrees with itself. Some of the universe's oldest stars serve as ticking cosmic clocks, their ages revealing secrets about the expansion rate of space itself. The cosmic chronometers method taps into these ancient galactic relics, measuring how long they've been burning to independently calculate the Hubble constant. Unlike techniques that rely on brightness or distance ladders, this approach studies the subtle color shifts in starlight from massive, aging galaxies to gauge how quickly the universe was expanding when those stars first formed. It's like reading tree rings, but on a galactic scale, each hue change in their spectra marking billions of years of cosmic history. Yet when researchers compare these age-based expansion rates to other methods, the numbers refuse to fall in line, creating yet another jagged edge in our understanding of the universe's growth. The magic lies in a phenomenon called redshift drift. As galaxies age, their stellar populations evolve predictably. Massive blue stars die young, leaving behind longer-lived red stars that dominate the galaxy's color over time. By analyzing spectral features like the 4,000 angstrom break, a telltale dip in light intensity caused by older stars' metal absorption, scientists can estimate a galaxy's age at different cosmic epochs. Pair this with its redshift, how much its light has stretched due to expansion, and voila, you get a direct measurement of how fast space was stretching between when the light was emitted and now. The larger the age-redshift mismatch, the faster the universe must have grown. But the chronometers have been ticking out conflicting timelines. Studies using data from the Sloan Digital Sky Survey found galaxies 9 billion years old, pointing to a Hubble constant around 67, comfortably matching the cosmic microwave background's sluggish expansion rate. Yet when other teams applied the method to closer, younger galaxies, the numbers ballooned toward 73, aligning with local Cepheid measurements. This bizarre time-dependent split implies either the universe's expansion accelerated unevenly across cosmic epochs, or more troublingly, that ancient galaxies aged differently than our models predict. One leading suspect is metallicity, the heavy element content of stars. Older galaxies tend to be metal-poor, and their spectral features evolve more slowly than modern, metal-rich ones. If astronomers underestimate how metallicity affects the 4,000 angstrom break, they might misjudge galactic ages by hundreds of millions of years, skewing the inferred expansion rate. A 2022 calibration error revealed this exact pitfall. When researchers accounted for variable metal abundances across cosmic time, some chronometer-based Hubble constants shifted by up to 5% overnight. Another wrinkle comes from galaxy mergers. When two star systems collide, a common occurrence in the early universe, their mixed stellar populations can mimic the spectral signature of an older, single-generation galaxy. The illustrious TNG simulation showed that unaccounted-for mergers might make galaxies appear 1 to 2 billion years older than they truly are, potentially explaining why chronometers from the universe's teenage years skew toward slower expansion rates. This cosmic case of mistaken identity could mean we've been misreading the universe's growth spurts from fossils that are more scrambled than we realized. The most tantalizing possibility: chronometers might be capturing real variations in the Hubble constant across time. If dark energies push against gravity strengthened relatively recently, cosmologically speaking, older galaxies would naturally record a more sedate expansion rate than modern measurements show. This would make the chronometer conflict not an error, but a smoking gun for evolving dark energy models. Upcoming surveys like the Dark Energy Spectroscopic Instrument aim to test this by mapping millions of galaxies across 11 billion years of cosmic history. Until then, these stellar timekeepers remain both our most direct window into the universe's expansion history and yet another piece of the Hubble tension that refuses to fit neatly into place. Galaxies aren't just passive passengers riding the cosmic expansion, they're also surfing hidden rivers of gravity, pulled by invisible currents that could be muddying our measurements of the universe's growth. These large-scale flows, known as peculiar velocities, arise from regions of space where matter is piled up or spread thin, creating gravitational tides that tug entire galaxy clusters off course. Picture a leaf floating down a stream. While the water's flow carries it steadily forward, akin to cosmic expansion, eddies and whirlpools, the gravitational pull of surrounding matter, can send it veering sideways. This extra motion doesn't just add noise to our data. It might be systematically biasing local measurements of the Hubble constant, making nearby galaxies appear to recede faster or slower than the true expansion rate. The scale of these motions is staggering. Our entire local group of galaxies, including the Milky Way, is being dragged toward the Virgo cluster at nearly 600 kilometers per second, a flow amplified by the even more massive Laniakea supercluster's gravitational pull. When astronomers measure distances to nearby galaxies using Cepheid variables or supernova, these peculiar velocities get baked into the observed recession speeds, potentially skewing the inferred Hubble constant by up to 3%. That might sound minor, but it's half the gap between the dueling expansion rates from local and early universe measurements. A 2020 analysis of over 1,000 supernova found that failing to account for these flows could inflate the local Hubble constant by as much as 2 kilometers per second per megaparsec, just enough to turn a subtle tension into a full-blown crisis. The real puzzle lies in disentangling these motions from true cosmic expansion. Peculiar velocities leave a distinct fingerprint. Galaxies in overdense regions like the Great Attractor's pull should show slightly blue-shifted spectra moving toward us against the expansion, while those in underdense voids exhibit extra redshift. Teams like the Cosmic Flows Project have mapped these flows using galaxy surveys, revealing a cosmic web where some filaments race toward us while others flee faster than pure expansion would predict. Yet when scientists subtract these flows from local Hubble measurements, the tension doesn't fully resolve, suggesting peculiar velocities might be masking an even deeper discrepancy. One provocative explanation is that we're caught in a quiet region of the cosmos where flows are unusually tame. Most local measurements rely on galaxies within a few 100 million light-years, a volume that might not fully sample the universe's true velocity field. A 2023 simulation showed that if we inhabit a pocket where outflows and inflows happen to balance, our local Hubble constant could appear artificially high or low compared to the cosmic average. Supporting this, the KBC void, a local underdensity spanning 2 billion light-years, could be suppressing inflow velocities, making near-by expansion seem faster than it truly is. But the plot twist comes from galaxies at the edges of these flows. The most distant Cepheid hosts, like NGC 5584, show peculiar velocities aligning with cosmological models, yet their Hubble constants still disagree with the CMB. This implies that while flows might amplify the tension locally, they can't wholly explain why early and late universe measurements diverge. Upcoming surveys like the Mauna Spectroscopic Explorer aim to map peculiar velocities across billions of light-years, testing whether these cosmic currents are the missing piece or just another red herring in the Hubble tension mystery. Until then, one thing is clear: the universe isn't just expanding, it's swirling with hidden motions that could be rewriting the rules of our cosmic map. Long before galaxies filled the cosmos, the universe endured its most dramatic transformation since the Big Bang, the epoch of reionization. This cosmic dawn, when the first stars and galaxies ignited, burned away the primordial fog of neutral hydrogen that had shrouded space in darkness. The timing and duration of this upheaval hold crucial clues about the Hubble constant, encoded in the faint afterglow of the cosmic microwave background and the absorption patterns of ancient quasars. Yet when researchers piece together this cosmic crime scene, the evidence paints conflicting pictures of how fast space was stretching during these formative years. The key lies in how reionization sculpted the CMB's polarization. As ultraviolet light from the first stars ripped electrons from hydrogen atoms, the freed particles scattered the CMB photons one last time, imprinting a distinctive swirl pattern called B-mode polarization. The Planck satellite's measurements of this signal suggest reionization began around redshift 12, about 300 million years after the Big Bang, and lasted roughly 500 million years. Plugged into cosmological models, these dates point to a Hubble constant near 67, snugly matching the CMB's own expansion rate. But this creates a paradox. If the universe was expanding that slowly during reionization, why do local measurements find it's now racing apart 15% faster? Quasar spectra add another layer of mystery. The light from these distant beacons bears the fingerprints of intervening hydrogen clouds, showing patches where the gas was still neutral versus ionized. By counting these Lyman alpha forest absorption lines across different cosmic epochs, astronomers can reconstruct reionization's progress. Surprising findings from the Sloan Digital Sky Survey reveal the process might have been patchier and more prolonged than CMB data implies, with some bubbles of neutral hydrogen persisting until redshift 5.5. This extended timeline would require faster early expansion to give structure formation a head start, pushing the inferred Hubble constant toward 70, uncomfortably close to today's local measurements. The tension escalates when comparing reionization constraints to other cosmic milestones. The James Webb Space Telescope's discovery of unexpectedly massive galaxies at redshift 10 suggests star formation began explosively early, a scenario that aligns better with faster expansion rates. Simulating such precocious galaxy growth under Planck's sluggish Hubble constant requires tweaking star formation efficiency to implausible levels. Meanwhile, the EDGE's experiment's controversial detection of anomalously cold hydrogen gas at redshift 17 hints at interactions with dark matter that could only occur if expansion rates were higher during cosmic dawn. These contradictions force us to confront a radical possibility. What if reionization wasn't a single uniform event, but a staggered process shaped by regional variations in expansion speed? Local density fluctuations could have created islands where reionization occurred earlier or later, leaving conflicting imprints in different probes. Alternatively, dark energy's influence might not be constant. A slight early boost in expansion could explain both rapid structure formation and the CMB's low Hubble value if it tapered off before recombination. As next-generation telescopes like the Square Kilometre Array prepare to map the hydrogen distribution of the infant universe in 3D, the reionization anomaly stands as both a puzzle and an opportunity. It offers a rare window into a time when the universe's expansion rate wasn't just a number in an equation, but a director shaping the very first acts of cosmic creation. Whether this data ultimately reconciles the Hubble tension or deepens it, one truth is already clear: the dawn of light in the cosmos holds secrets that could redefine how we measure its growth. The Hubble tension isn't the only cosmological headache keeping astronomers up at night. There's another anomaly lurking in the shadows, one that might be intimately tied to how fast the universe is expanding. Meet the S8 tension, a stubborn discrepancy in how much matter clumps together across the cosmos. On paper, S8 describes the density of matter in the universe and how tightly it's woven into cosmic structures like galaxy clusters. But when scientists measure it using two different methods, just like with the Hubble constant, the numbers refuse to agree, creating a parallel crisis that could hold the key to unraveling both mysteries. The conflict starts with how we probe large-scale structure. One approach uses the cosmic microwave background, where tiny temperature fluctuations reveal how matter was distributed in the infant universe. Plug these primordial patterns into our standard cosmological model, and they predict an S8 value around 0.82, meaning matter should be fairly loosely clustered today. But when astronomers actually map the modern universe's structure using weak gravitational lensing, the way galaxy clusters warp light from background objects, the observed clustering jumps to 0.76. That 6% gap might seem small, but statistically, it's even more significant than the Hubble tension, with odds of a fluke at less than 1 in a million. Here's where things get intriguing. These two tensions might be opposite sides of the same cosmic coin. The Hubble conflict suggests the universe is expanding faster than early conditions predict, while the S8 mismatch implies matter isn't clumping as strongly as it should. If dark energy is somehow stronger than we thought, pulling space apart more vigorously, it could simultaneously speed up expansion and suppress the growth of cosmic structures by flinging matter apart before gravity can fully assemble it. Simulations show that tweaking dark energy's equation of state to W equals -1.1, leaning into phantom territory, could alleviate both tensions at once, nudging the Hubble constant upward while lowering S8 toward observed lensing values. But dark energy isn't the only suspect. Alternative gravity theories, like those where Einstein's equations break down on cosmic scales, can also link these anomalies. In some modified gravity scenarios, the enhanced gravitational pull needed to explain galaxy rotation curves without dark matter would also reduce matter clustering on large scales, potentially reconciling S8 measurements while indirectly affecting the Hubble constant through altered expansion histories. The catch: most of these models struggle to match both tensions simultaneously without breaking other well-tested physics. The most tantalizing clue comes from galaxy surveys like DS and Chi-DS, which found that the S8 tension seems to evolve with cosmic time. At redshifts around 1, when the universe was half its current age, the clustering measurements align neatly with CMB predictions. It's only in the local, present-day universe that the discrepancy emerges. This timeline suspiciously mirrors the Hubble tension's own progression, where early universe probes CMB, BAO agree with each other but clash with local measurements. Together, they paint a picture of a cosmos that might have started playing by different rules sometime in the last few billion years. A shift so subtle we're only now detecting its echoes across multiple independent observations. Whether these anomalies ultimately point to new physics, systematic errors, or something even more unexpected, their intertwined nature suggests we're not dealing with isolated glitches but cracks in the foundation of modern cosmology. Solving one won't just patch a hole in our understanding. It might tear open an entirely new window into how the universe truly operates. And that's the real mystery lurking behind these numbers. Not just why they disagree, but what they're trying to tell us about the unseen forces sculpting reality itself. The universe's greatest unsolved mysteries rarely stay that way for long, not with an arsenal of next-generation telescopes poised to rewrite the rules. As the Hubble tension festers, missions like the Nancy Grace Roman Space Telescope and ESA's Euclid are gearing up to attack the problem from angles we've never tried before. Roman, set to launch by 2027, isn't just another observatory. It's a cosmic census machine, engineered to map millions of galaxies with a field of view 200 times wider than Hubble's. Its secret weapon, a relentless focus on Type Ia supernova and infrared bright Cepheid variables, observed free of the dust distortions that plagued prior measurements. By capturing these celestial yardsticks across vast swaths of the cosmos, many in galaxies too distant or dim for Hubble to resolve, Roman could finally determine whether the Hubble tension stems from local calibration quirks or a genuine cosmic rift. Euclid takes a different tack. This European space telescope, already cruising at Lagrange point 2, is hunting for answers in the shadows, literally. Instead of stars, it traces the invisible scaffolding of dark matter and dark energy by measuring how their gravitational grip warps the light of billions of galaxies. Its precision maps of weak gravitational lensing and baryon acoustic oscillations will test whether dark energy's strength has changed over time, a potential smoking gun for the Hubble discrepancy. Early data hints at something peculiar. Galaxies in Euclid's deep field images appear slightly more clustered than standard cosmology predicts, as if an unseen force tweaked the universe's expansion history. If confirmed, this could mean the Hubble constant was never constant at all but a variable rhythm in the cosmic symphony. Then there's the Vera Rubin Observatory, a ground-based behemoth in Chile set to begin its 10-year legacy survey of space and time in 2025. With a 3.2 gigapixel camera scanning the entire southern sky every few nights, Rubin will catch transient events like supernova and kilinovae in numbers that dwarf all previous surveys combined. Its real power lies in statistical brute force. By tracking how these explosions fade across different cosmic epochs, Rubin could reveal whether expansion rates vary not just between the early and modern universe, but patch by patch across the sky. Already, simulations suggest its dataset might uncover Hubble bubbles, regions where local matter density skews expansion measurements, or even stranger anisotropies. Yet these missions carry their own blind spots. Roman's infrared focus, while bypassing dust, risks misjudging Cepheid distances if their metallicity effects are more complex than models account for. Euclid's lensing maps depend on precise knowledge of galaxy shapes, which could be biased by unforeseen quirks in star formation or black hole activity. And Rubin's breakneck observing pace might sacrifice the meticulous calibrations that Hubble and Webb painstakingly perfected. The stakes couldn't be higher. If these projects converge on a single Hubble value, it could crown a victor in the decades-long debate. But if they deepen the discrepancies revealing expansion rates that shift based on which celestial ruler you use, we may be forced to confront an even more radical truth, that the universe's growth can't be captured by any single number, but demands a bold new framework to make sense of its contradictions. The coming flood of data won't just resolve the Hubble tension, it will redefine how we measure the cosmos itself. Whether through Roman's galactic cartography, Euclid's dark energy autopsies, or Rubin's real-time cosmic pulse check, one thing is certain: the next chapter of this mystery won't just fill gaps in our knowledge. It will tear them wide open. Among the boldest attempts to explain the Hubble tension lies a hypothesis so radical it redefines reality's building blocks. What if dark matter isn't just an inert cosmic scaffold, but an active participant in the universe's expansion? This isn't science fiction. Teams at CERN and Fermilab are now seriously modeling interacting dark matter, where these shadowy particles don't just gravitate but exchange hidden forces with dark energy or even ordinary matter. Picture two invisible cosmic fluids, dark matter and dark energy, engaged in a subtle tug of war across billions of years. Early in the universe, dark matter's gravity dominates, slowing expansion. But if dark energy gradually siphons energy from dark matter through undiscovered interactions, the balance could shift unpredictably, creating the apparent mismatch between early and modern expansion rates. A 2023 simulation showed that just a 1% energy transfer could skew the Hubble constant by enough to bridge the observational gap, all while leaving the cosmic microwave background's pristine patterns intact. The implications spiral into stranger territory with decaying dark matter theories. If some fraction of dark matter particles spontaneously disintegrated into lighter particles, or even pure energy during the universe's middle age, the sudden loss of gravitational glue would have triggered a burst of accelerated expansion. This cosmic speed bump would leave modern measurements pointing to faster growth, while the CMB capturing the pre-decay era would reflect the original, slower rate. Intriguingly, telescopes might already have spotted echoes of this event. The Edge's experiment's detection of anomalously cold hydrogen from cosmic dawn could signal dark matter particles dumping their energy into the primordial gas, a thermal fingerprint of their disappearance. If confirmed, it would mean the Hubble tension isn't a measurement error, but the ghostly afterimage of dark matter's midlife crisis. Then there's the multiverse gambit. While parallel universes sound like comic book fodder, serious cosmologists are exploring whether our observable cosmos might be a rare bubble where dark energy strength deviates from the multiversal norm. In this scenario, most universes have way more dark energy, causing them to inflate so fast that stars and galaxies never form. We happen to inhabit an unusually sluggish bubble where expansion is just slow enough for life to emerge, but fast enough to perplex astronomers. String theory lends mathematical weight to this idea, with its landscape of possible vacuum states corresponding to different dark energy densities. The Hubble tension, then, becomes a cosmic selection effect. We measure an expansion rate that seems improbable because we couldn't exist in the more typical, sterile universes. The most mind-bending proposal involves time itself. Some quantum gravity models suggest the flow of time might have been fundamentally different in the early universe, not just slower due to relativistic effects, but operating under altered physics where constants like the Hubble parameter weren't fixed. If time's ticking was less regular near the Big Bang, our assumption of a continuous, uniform expansion would be catastrophically wrong. Imagine trying to reconstruct a symphony's tempo when the metronome's speed kept changing. That's the challenge cosmologists face if early universe clocks ran on different rules. Supporting this, certain loop quantum cosmology models produce Hubble values that naturally bifurcate into early and late regimes without contradicting other observations. What unites these radical ideas is their willingness to tear at cosmology's seams. Where most anomalies invite tweaks around the edges, the Hubble tension's persistence has forced physicists to ask whether we've misjudged reality's framework altogether. The coming decade will test these visions with unprecedented rigor, from particle colliders hunting dark sector interactions to telescopes mapping the universe's expansion in 4D. Whether the answer lies in shadowy particles, branching timelines, or something even stranger, one truth is already clear: the cosmos is daring us to think bigger. 25 cracks in the cosmic rulebook, each one a whisper that our understanding of the universe might be built on incomplete foundations. From mismatched Cepheid variables to rebellious quasars, from phantom dark energy to neutrino conspiracies, these anomalies aren't just glitches in the data. They're signposts pointing toward something profound, something that could redefine cosmology itself. The Hubble tension isn't a single puzzle, it's a constellation of contradictions, each suggesting that the universe's expansion isn't just a number, it's a story with chapters we've yet to read. Take the way local measurements clash with the cosmic microwave background. Cepheids, supernova, and red giants all scream that space is stretching faster than the afterglow of the Big Bang predicts. Meanwhile, baryon acoustic oscillations and weak lensing quietly side with the CMB, as if the universe can't decide how fast it's growing. Add in wildcards like gravitational lensing time delays hovering stubbornly between the two camps, and you're left with a cosmic Rorschach test where every observation reveals a different truth. The implications ripple far beyond academic debate. If these anomalies hold, we might be staring at physics beyond the standard model: dark energy evolving over time, invisible particles tweaking expansion, or gravity itself working differently on cosmic scales. Some theories flirt with multiverses or cosmic bubbles, while others suggest the Hubble constant was never constant at all. Even the most conservative solutions demand we rethink how we measure the cosmos, from recalibrating stellar yardsticks to questioning whether light itself tells the whole story. This isn't just about fixing a number, it's about rewriting the narrative of cosmic history. The tension could mean our universe hit an unseen accelerator a few billion years ago, or that we're misreading the cosmic clock altogether. Perhaps the most thrilling possibility, that all these anomalies are threads of a larger pattern, one that ties dark matter, dark energy, and the birth of galaxies into a single, transformative framework we've yet to imagine. So where do you think the answer lies? Could sterile neutrinos, phantom energy, or modified gravity crack the code? Or is there a wild-card theory no one's dared to propose yet? Drop your favorite ideas in the comments, because this mystery isn't just for astronomers. It's for anyone who's ever looked up at the night sky and wondered what secrets the cosmos is still keeping. And if history's any guide, the solution won't just resolve the tension, it'll reveal a universe stranger and more magnificent than we ever dreamed.